Hello and welcome to a new problem solving session. You can see a problem at your screen that is about a charged soap bubble, and the statement of the problem is simply a soap bubble of mass m equals 0.01 gram has a coefficient of surface tension sigma that is also 0.01 Newton per meter, and mass and coefficient of surface tension is given. The bubble has been inflated through a short thin tube and initially, and then the bubble is charged with an electric charge Q. The value is given in coulomb, and the tube remains open. That means tube has not been detached and it is open. Determine the equilibrium radius R0 of the bubble. And secondly, we need to determine a period of a small spherical oscillation of the bubble. So there are two things here. First, we are going to consider the pressure exerted on the soap bubble due to electrostatic forces once the charge is being distributed over its surface. So, to find out the electrostatic pressure exerted on the bubble after distributing the charge, we must consider a small element, very small element, a very small patch, you can say, name it as delta S on its surface. And just a point outside it, just a point outside the bubble, that is that we would like to consider like a hollow sphere, a spherical surface charged uniformly by a charge Q. The electric field here is E, and this is E composed of two kinds of electric field. That is the electric field due to this surface element and the rest of the hollow sphere, rest of the spherical surface. And these two electric fields, namely the electrostatic field E0 due to the rest of it, and the electric field due to this a small part of the surface, both are same. And if I call their value as E0 and E1, both are same. And basically, from the study of your electrostatic books, this twice E0 and E1 is same. So you can write here twice E0 will be equal to E. That means E0 is equal to E1 is going to be half of 1 by 4 pi epsilon naught Q by R square. This will be the electric field produced on this a small element delta S. And so the force exerted on the bubble will be simply charge on it, force on the bubble, electric force on the bubble. I would like to write it Fe. That will be the charge, a small charge on this a small element delta S, multiplied by E0 or E1, whatever you would like to say. And this delta Q can be written as simply by Q by 4 pi R square, charge per unit area, multiplied by delta S, and just multiply is by E0 in continuation. And you can see the force, we have just calculated the force exerted on the small element delta S of the bubble. And of course, then the electrostatic pressure acting on the bubble, that I would like to call it PE, the electrostatic pressure acting on the bubble, and this can be simply written as force per unit area. And its value, if you calculate them, you will get q square by 32 pi square epsilon naught r to the power 4. And the pressure difference due to surface tension on this surface will be in this direction, and its value is definitely 4 sigma by r, because it's a SO bubble, and its radius is r. So the net pressure being net pressure, we can write P, and that P will be equal to P plus P pressure due to surface tension. I would like to call it P sigma. And so in equilibrium, this net pressure is going to be 0, and you can write that q square by 32 pi square epsilon naught r naught. Equilibrium radius is r naught, so I'm going to call it r naught simply, and minus 4 sigma by r naught, that will be equal to 0. And you can find here the value of equilibrium radius, and if you can calculate all those things, you are going to get something like r naught equals third root of q square by 128 pi square epsilon naught sigma, and put the values and get your answer. I think it will be approximately 3 centimeter. And next part of the problem is in fact I'm more interested in next part of the problem, that was something like determine the period of a small spherical oscillations of the balloon. That means the bubble radius deviates from its equilibrium value or not. And suppose that its new value, its new radius becomes, when disturbed from the equilibrium value, equilibrium radius, its value becomes r simply. So that I can write r minus r naught becomes delta r. Delta r is quite small, very small. And I'm talking about the same element surface delta s. And now the force becomes pressure multiplied by delta s. And I would like to write this pressure in terms of like this was the original pressure, and from here I can calculate simply that force sigma will be equal to q square by 32 pi square epsilon naught r naught cube. This is force sigma, and you can say the pressure now becomes since the radius changed, so the pressure value becomes, instead of r naught, it becomes r 4 by 4. And so this can also be changed, and it will be simply 4 sigma by r, and this is not equal to 0 right now. So I would like to write this pressure, this pressure thing as the first term I would like to write as 4 sigma, and it will be written as 4 sigma r naught cube by r to the power 4. Putting the value of 4 sigma from here in this equation, I can write it the first term as 4 sigma r naught by r4, and the second term is simply 4 sigma by r. So this is the pressure thing, and if multiplied by delta s, it will become the force. and so that the new expression for the force simply becomes 4 sigma uh, r naught cube by r raised to 4 minus 1 by r delta s, and this is the force. And this delta r is quite small. For convenience, I can write here delta r is very much less than r naught, and then this force can be simply written as dp by dr at r equals r naught multiplied by delta r. This pressure thing can be written like this, and when multiplied with delta s, this force can be expressed like this. And the mathematics, how to calculate the things, how to calculate the differentiation, and you are simply going to get something like 4 sigma delta r delta s. And after putting the values, after making the differentiation, taking the derivative and putting r equals r naught, you will get minus 4 r naught cube by r raised to 5. And oh no, I have not put, I'm just making a differentiation. R naught is constant, so I can write it like 1 by r square differentiation, and I need to put r equals r naught yet. And finally you are going to get the result as minus 12 sigma by r naught square. I have now put r equals r naught, and I got something like this force as this, in this form. And the minus sign simply shows that the bubble is stable, equilibrium is stable. And from this we are going to get the value of k, and k is simply I need to put down the value of delta s also, so that or I can write it here. I will try to calculate f equals if I'm comparing this result to f equals minus kx, I would like to write k equals 12 sigma by r naught square delta s. And the mass of this small element delta s, it can be simply written as m by total mass of the bubble is m, that is given in the problem, by 4 pi r naught square multiplied by delta s. So we are going to get the omega equals simply under root k by m, and its value you can see here is pi m upon 12 sigma. And this is the angular frequency. No, I made the mistake perhaps. K by m will not come like this. K by m will be like I'm putting all the values, 12 sigma by r naught square multiplied by 4 pi r naught square by m. This is k by m. And now after removing all those terms, we can get time period, and time period will be 2 pi by omega. And you can see here this thing becomes simply pi m by 12 sigma, and this is the time period required in this problem. Thank you very much for watching.